Our next application comes mainly from computer science. We want to search trees, meaning that we want to find a systematic way of going through all the vertices in a tree. Why would you want to do that? Well, most often you have some information stored in a tree-like structure, maybe lots of data stored in a hierarchy of files or folders, and you want to find the precise piece of data that you're looking for. And of course, if you have a small tree, you can just look, but the idea is that this is most useful if you have thousands of vertices in a tree. Another fun way to look at this is that this is the way that hereditary monarchies work. So if you have the family tree of a monarch in a monarchy, then you want to see who will be king or queen next, and then you apply some sort of tree search to find the next candidate. There are two methods to search through trees. Well, there are many, but the two probably most known ones are breadth-first search and depth-first search. So we'll go through how these work. Before we do that, remember that we have shown that in a tree between any two different vertices, not only is there a path, but there is a unique path. So this might be useful to keep in mind. With this in mind, if you have a rooted tree with a root R, so remember it's a tree where you have chosen a vertex that you call the root, then between any vertex different from the root, there's a unique path, V, V1, etc., coming to the root. And so just to introduce some terminology, the vertex V1 is called the parent of V, and you call V a child of V1. So you imagine some sort of family tree, and then the root is somehow the oldest ancestor, and any person has a parent. Well, because of the way trees work, any person has a unique parent, but one parent might have multiple children. So how does breadth-first work? In breadth-first search, you start at the root, and now you want a systematic way to visit all the vertices in the tree. So first you visit all the children of your root, so everything that's adjacent to R. Once you've gone through all those, then you go one step down and search through all their children, and one step down and search through all their children, and so on, layer by layer, until all vertices are visited. The key notion here is the notion of a distance. So the distance between two vertices is the length of the shortest path between these two vertices. Since we are in a tree, it's actually the length of the unique path, so the number of steps in the unique path between these vertices. And one way to phrase how BFS, or breadth-first search, works is that all vertices at a given distance m from the root are visited before any vertex at distance m plus 1. So let's see how this works in an example. So here is the algorithm that I've just copied. So you start at the root R. Now the way I have drawn the tree, I'm meaning that this is 1. Then I visit all the children of R. So these ones. The order in between these is not part of the algorithm. There might be other ways to choose exactly which one to visit first, but you visit those in some order. Then you visit all unvisited children of the visited vertices. So now all the children of this visited vertex are visited. So you go through the unvisited children of 2. 3 has no children. 4. And you continue on to the next layer, and so on. So the important thing is that you go layer by layer, so to speak, increasing the distance to the root only once you have visited all the vertices at the same distance. This is actually the way that in some monarchies the next king is selected. In Saudi Arabia, for example, there was an original king, and then the next king is one of his sons, and when a king dies, his brother inherits the throne, and so on, until all the brothers have died, and then you go to the next generation. The other way of searching a tree is depth-first search. The idea in depth-first is the opposite of breadth-first. So you start from the root, and you go along one path as long as possible. And once you reach the end, you backtrack step by step until a new path opens and you go along that. Formulated in terms of an algorithm, you start at the root r, and for each child of the root, you visit the child, and then if v has children, you repeat this for the tree that has v as its root. I will explain in the example what this means and why this makes sense. And once you've finished, you stop, and first at that point you move on to the next neighboring vertex. So let's see how this works for the same tree we had previously. So again, you start here at this root 1. Now for each child, so let's choose a child to start with, maybe this one. We visit it. And when you have a rooted tree, each vertex induces a subtree that has this vertex as its root. So you have this part is somehow a tree of its own, and it is there that we repeat this. So we repeat the process. For each child, you visit the child, and you look at the tree that this child creates. For each child, you visit the child. Now this child has no children, so we cannot continue, we stop. And then we go to the next vertex. This is ensured by the algorithm because now I have emptied this branch, and then once I am done with a child, once I'm done, I visit the next child. This is what the for each child part means. In practice, I backtrack until a new path opens and I select that. Now this branch is done. Then I go back, I unnestle my loop to the previous one. This is the next one. Then I go up all the way back. This one has no children. Go all the way back. This one. Continue all the way down. Go all the way back. And like so. So I have now performed this depth first search for this tree. And this is the way that monarchs are elected in some systems, for example, the British Crown. So when a monarch dies, their son or daughter inherits the throne. And if they are already dead, the throne doesn't go to any brother, it goes to their children, and so on, until there are no children to find. Then you go back to as little as possible and search a different